Good afternoon. My name's Peter Lawrey, and from CEO of Chronicle Software, and today I'll be talking about some of the scalability issues to do with blockchain and also some of the proposed solutions for this. So my background is that I'm a Java champion. I've got the most answers in the world for Java and the JVM. I've also been working with investment banks and hedge funds for many years and 25 years in IT. I have my own company now. I've been running for 4 years and we've got 14 employees or staff. So our background in terms of Chronicle Software is in microsecond latency services, typically 1 to 2 digits of latency in Java. And one of the key elements of these systems is usually this persisted shared memory. An example of which, the sort of latencies that we tend to work with can be sub-microsecond, even up to 1 million messages per second. And all this in pure Java. So it was something of an interest of mine so why is it the blockchain can't be a lot faster than it is? What are some of the inherent reasons why it is slower? So what is blockchain and why is it hard to scale? So a blockchain is, to some degree, a cryptographic linked list of blocks. Each block contains multiple transactions, and each block refers to the previous block of transactions or the hash code of the previous block of transactions. And by building up this chain, it becomes increasingly difficult to attempt to alter the chain as more and more chain items are added, as more and more blocks are added. But conceptually, it's a linked list where you've got one block, each one refers back to the previous one, and as you keep adding more and more onto the list, it becomes harder and harder to attempt to alter any of the previous nodes in the list. And that gives you a distributed immutability. So as opposed to a centralized database of ledger of transactions, it's decentralized, but it's not distributed, and that's an important distinction. So it's decentralized in the sense that the ledger itself is running across a large number of nodes, possibly all over the world, but every node still has to be able to process every transaction. So in reality, it's physically distributed, but logically it's centralized. Logically, everything has to be serialized onto this chain. It's not a tree, it doesn't expand. There's a sequence of transactions that occur in a particular order. So what kind of throughputs do we need in the financial world? Well, in IoT, you get various numbers thrown around. They're usually in the hundreds of thousands of transactions per second. Whether IoT messages need to go into blockchains or not is one question. But, or in fact, how much volume IoT will eventually have can be quite high. You could be potentially in the order of 1 million messages per second. But what's actually being done today? Well, Visa is one of the largest transaction networks. It's financial. And it's getting an average of 150 million a day, which is a sustained rate of about slightly under 2,000 a second. But at its peak is around 24,000 a second. That's what it's capable of. So it's interesting to note is that it has enormous capacity to handle bursts of activity, such that you get something like 10 to 15 to 1 capacity compared to what its sustained rate is. So there's a lot of headroom to be able to cope with bursts of activity. And in particular, if all you do is invent a transaction system that's as fast as Visa, that might be nice. You might be able to compete with Visa on price, but it's not really compelling from a performance point of view. You may be able to compete on other attributes, but you couldn't say that you can outperform Visa. So what do we actually achieve though? So these are two of the most common blockchains. They both use Proofofwork, which is fundamentally slower. And Ethereum gets about 7. so quite a bit lower than either the 2,000 or the 24,000. And Bitcoin gets around, in reality, about 2.7 transactions per second. So we've got a long way to go to even compete with Visa, let alone replace it, certainly on throughput basis anyway. So what are some of the ways you could solve this? Well, in the web space, if you want to increase your throughput, you can add horizontal scalability. You add more and more nodes, and the system becomes faster in terms of the amount of throughput it can do. The latency doesn't come down. The time it takes to deal with any particular request isn't any faster, but you can handle more users and more requests. So you can get order n scalability. So you can get, or in theory, in practice, it's sometimes a little bit less. In specific cases such as Bloom filters, you can actually achieve superlinear scalability by having nodes effectively specialize the queries that they're coping with. So you can actually get slightly better than n, but that's the sort of area that you're aiming for and you're likely to be able to achieve. And as a result, the sort of numbers of nodes that you typically have for a widely used service might be in the hundreds, could be in the thousands. Google have many more than that, but it's not unusual to see a web service that's running across hundreds of machines. Transaction systems, however, because they also have somewhat serial nature, you can't necessarily process a transaction until previous transactions have been processed. They have a particular order and their success determines on that order. You can scale them a little bit by separating them by instrument or by symbol. So for example, in foreign exchange or currency exchange, you can separate out, say, euro-dollar transactions, which is euro for dollar, against, say, sterling for dollar transactions. But the problem is that certain instruments are much more abundant than others. And so your limiting factor is how much activity you can get with the most busy symbol on one machine. You can't split that busy symbol across machines very easily. So that becomes your limiting factor. And what happens is that your activity level dies away pretty rapidly. So the top 8 currency pairs account for most of all the transactions, even though there's about 400 tradable on many exchanges. 8 of them account for pretty much everything. Fixed income is even more extreme. Basically, if you look at UK government bonds, there is one kind of instrument, which is a 3-month instrument. It has more activity than every other UK bond combined. So you put that on one machine, you put every other instrument on a second machine, you don't really achieve much more scalability than that. So you can achieve some scalability by adding more nodes, but it's not really a lot. What about blockchain? Well, blockchain has the opposite problem. As you add more nodes, it takes longer for them to reach consensus. So in fact, it goes down with the login. So this is a real problem. Not only that, is that Bitcoin is running in the order of hundreds of thousands of nodes. So as it increases in success and people run more nodes, the thing actually gets slower. And in many cases, the blockchain can take longer to come to consensus than it takes to actually compute the block, which is meant to be the most expensive bit. So, that's an obvious scalability problem. You've got uncontrolled number of nodes. The nodes themselves are not homogeneous. So unlike the previous examples, all your nodes are going to be more or less the same. You can pretty much determine, you can say, well, they're going to be the same operating system. They're probably going to be more or less the same hardware. You might have some older and newer nodes, particularly in the web space, but you can manage that. Usually the difference between your fastest and slowest node might be a factor of 2 or 4. But in Bitcoin, the driving factor is reducing power consumption. So some nodes will be running high-end server, some will be running lots of GPUs. In other places, power is expensive, so people will be running on Raspberry Pis. You've got no control over the hardware, and that variety of hardware means that slower nodes can slow down the entire network because they're trying to just keep up. So adding more nodes doesn't help. So one option is, can we use faster nodes? Well, in the web space, you generally don't need to have higher nodes because you can do horizontal scalability. Generally, you will take the sort of moderately good nodes and you'll just put in more, and that works out to be the cheapest solution. In trading, you generally want to have a small number of very fast machines. GPUs have some limited use case, but in general, because you don't have high degrees of scalability, GPUs don't work quite so well, because if you've got 1,000 cores, but you can only keep 1 or 2 of them busy anyway, they're not very useful. Bitcoin actually has, if you're using proof of work, there's actually a metric in there that works out how fast it takes to compute a block, and it adjusts itself. So the aim is to take around 10 minutes of computing time. So as more computing time comes in, it makes the problem harder. So the problem just keeps expanding to adjust so that it will take 10 minutes to compute the block. So as you put in faster machines, the problem just gets harder. So faster machines isn't going to help the system as a whole. You can help you personally because you might allow you to mine more, but if too many people have these faster machines, the whole problem itself becomes harder. So adding faster nodes doesn't really help the overall system because there's a fundamental threshold of 10 minutes that each block takes to compute. So another option for improving performance is to use some batching. In web space, this is fairly common for back-end services, for databases, to batch up transactions to improve throughput. In trading systems, this has some limited benefit. It's more often that you'll use something like conflation, where if you're getting lots of market data coming through, you just take the latest market data, which is a kind of batching because it just replaces all the previous market data. Now in Bitcoin, it has a particular block size. So each block is fixed by the number of bytes that can appear in a block. So bigger transactions mean that you can't have as many transactions in a block. The transaction size, the number of bytes in a transaction actually matters, and you actually get charged proportional to the number of bytes in the transaction as a fee. Now, for a long time, it's been fixed at about 1 megabyte. Changing it isn't so much a technical issue as it is a political one, and finally, the consensus has become that it should be 2 megabytes in size. But that only allows you to have double the number of transactions per 10 minutes, which doubles the throughput. So that means that instead of taking you're getting 2.5 transactions per second, you can now get about 5. It's not a huge, exciting increase. It's not some sort of breakthrough. It'll improve things, but it's not a breakthrough change. Can we use compression? So again, in the web space, particular images can be compressed dramatically. It makes such a difference. No one even considers sending uncompressed images unless they're tiny icons. Video is naturally compressed. You can compress the content of pages. You can also send bits of pages. So you don't send every element of the page every time. You break it up into bits, and only the bits that haven't been cached can be downloaded. Well, unfortunately, in the Bitcoin space or digital currency space, none of these are really available to, because with encryption, the idea is that the data is almost uncompressible because the data is by design pseudo-random, and as a result, you don't get much. There's some data that's not compressed, it's not encrypted. That could be compressed, but it's not going to make a dramatic change. In the trading space, there is some benefit in using compression, and particularly for WAN links. So if you're sending data across WANs, It's fairly common to use compression, but it has a small impact on latency. So unless you're sending data over a low bandwidth link, compression actually hurts you. So, for example, the FIX protocol has a protocol called FAST, which is a compressed form of FIX messages, but that takes computation time. So fast connections over a high bandwidth connection can actually be slower than not using compressed, because the extra time you spent compressing it and decompressing it was higher than what you saved by just sending the message. Green is good. This is less of a factor in a lot of people's decision making, but nevertheless, it's one worth highlighting because it gives you a stark contrast. So in the web space, when there's a large number of nodes, people start considering, well, how do I house it? Can I do this more efficiently? We tend to use the slightly less powered but more efficient servers anyway, so it encourages good use of hardware. In the trading space, they tend to have machines that are very highly powered. They drain more power per server, but because of scalability issues, you rarely see a lot of servers. However, in the proof of work space, it's only limited by economics. So the amount of money you can make is the only limiting factor as to how much power you consume. And in some places in the world, power is cheaper, which allows you to consume even more power and still make money. So as a result, it can end up using a lot of power. So has anyone got an idea of which one uses the most power, or most or least power here? Ireland, good, very good. Ireland uses the most, and Georgia uses the least. Bitcoin, all of Bitcoin is estimated to use about the same as Lebanon, and almost the same as Puerto Rico, which is without power at the moment. So, so as a result, you've got a system that's using as much power as a decent-sized country. It's estimated it's around $1 billion a year spent on electricity running Bitcoin. So it's a fairly substantial amount. The reason they do this, though, is that the miners can make around $4 billion a year. So the economics says, well, actually, you could probably drain even more power and still make money. But it is a system that encourages an enormous amount of power consumption as a result. So one of the proposed solutions, this is one of the most widely suggested solution, partly because this is a very simple change. You just increase the block size. It's not complex technically, it's more complex politically. Because a system like Bitcoin is not centrally managed, it can take a long time for enough people to agree that this is something worth doing, that everyone collectively will upgrade the size of each block. And then in November, I believe they will be switching from 1 to 2 megabytes, and that will double the potential throughput of Bitcoin. But as I mentioned, you're going to have to increase the block size an awful lot to really start competing with some of the other solutions. Now, one of the challenges to increasing the block size is that in Bitcoin, you can create an address at will. You can create your own addresses, and you can create an address for each transaction as one of the suggested best practices. That address then lives for the life of Bitcoin, which could be pretty much forever. So as a result, the database of addresses and how much each one of those is worth is growing, ever growing quite rapidly. And in fact, at the moment, it's estimated to run a Bitcoin system and keep track of all the balances, you require about 1 terabyte, which is then kind of hard to run on Raspberry Pi. So nevertheless, and by increasing the volume, you actually double the rate at which this database is expanding. So if you increase it by a factor of 10, the database is going to expand 10 times, potentially 10 times faster. So there is some downsides to the way it works, that just increasing the amount of transactions per second you can do isn't necessarily sustainable. So one of the most common proposed alternatives is a thing called proof of stake. Now, part of the reason people use proof of work, sorry about that. Part of the reason people use proof of work is that it doesn't require trust between the nodes. You're trusting in the amount of power that would need to consume, and you trust that there aren't any large organizations or governments that are willing to put in enough power to manipulate the system. And certainly Lebanon wouldn't be in a position to, even if they used all their power to really manipulate the system, it'd have to be a government with access to even more power than that, if they even wanted to. Proof of stake, however, actually doesn't require as much power consumption. Instead, you put up a certain amount of value, which is at risk, to run these nodes. So if that allows a certain element of trust. Because you have money at stake, people will trust that you don't want to lose that money if you violate it or you commit some fraud. And in particular, Ethereum, I believe, is looking to migrate to support proof of stake to increase their scalability. One of the downsides or side effects, depending on your point of view, is that proof of stake actually encourages a lot less nodes, because less nodes can just run as a part of the system, because they need to put up a certain amount of money. It may be that Ethereum, if they switch to proof of stake, you might have to put up hundreds of thousands of dollars worth. That clearly will mean that there's a lot less nodes who are in a position to do that, and that will reduce the number of nodes, which will also reduce the overhead of having so many nodes trying to run this system. But you could get a substantial improvement in throughput. Another widely suggested solution is to use what's called off-chain state channels. And this is where you have channels which are sort of working around the solution, that allow interconnection messages between individual parties that don't actually have to go via the block. So this is useful for messaging. So you could say, I'm willing to do this transaction for you at this price. Do you agree? No. What about this price? Okay, we'll go ahead. And then the actual fulfillment is done on the blockchain. But everything else, all that interaction that was going on previously, can be done separately at a much cheaper price, achieve much higher throughput, and it can be done privately as well. So one of the benefits and downsides of blockchain is that it's all public. And by being public, maybe some of those interactions, speculative interactions, you don't want to make public. So you can discuss prices, and then people can't front run you. So they can't just see that you're willing to do this trade, suddenly buy up something or sell off something, and therefore manipulate the price before you've got a chance to actually do the trade yourself. So it supports microtransactions. So you can, for example, put a deposit of $10 aside, and then every time you listen to another track of music, you give 1 or 2 cents to a music provider. It keeps coming out of the $10. And the worst that can happen is you'll lose it, so it's not as secure, but you might lose the whole $10, but that's the worst that can happen. You lose your deposit. But each one of those little transactions aren't costing so much money that it becomes non-economic. And this can see significant improvement. There's a number of solutions in this space. Another option is sharding or petitioning. So you can potentially split up the chain so that transactions that are occurring, say, from someone in the UK to someone else in the UK, don't necessarily have to go all the way around the world. Maybe they only need to be agreed amongst nodes that are in the UK. You can also split by purpose. So if you're providing different services, they don't necessarily have to all go via the same chain. And Ethereum also supports this by allowing you to run lots of different instances of Ethereum with their own coins, running completely independently. And if one of them's used a lot, it doesn't slow down any of the others. So you can see potentially significant improvements there from the petitioning. Most likely, I think all of these solutions will be looked at and implemented because it's a very broad space. There's something like 1,100 coins offerings out there at the moment. And between them, I think they will probably explore all of these options. So I think it'll be a very exciting space in the future, technically, in terms of what you can achieve in terms of throughput. And probably should have included in here a quote from the head of the IMF, who last week was quoted as saying that she could see a future where digital currencies actually replace traditional banking. So not just investment banking, but also retail banking. And since that's an enormous market, that could be a fairly dramatic change, both for end users, but also for banks in particular, or anyone working for them. So I think it's an area that banks are very aware that they need to invest in. They need to be part of it when this changes, even though they themselves aren't quite ready to use it. They've got some proposed solutions. Some banks are getting together to reduce cost of transaction in a number of areas, such as securities, most recently announcement between UBS and a couple of other banks. But I think in the next 5 years, it'll become much more ubiquitous and much more cross-bank. Thank you. I think we have time for questions.